lies, damn lies, and p-hacking. Previously we said we are dropping the demarcation problem and now trying to draw a line within science, an epistemically meaningful line between good and junk science. To do that, we said we will look at specific cases. We have already discussed cases of scientists cheating and getting caught, being falsely accused of cheating, and even what we called pathological science, a collective delusionary state in which some significant numbers of scientists see and report things that aren't real. In cognitive neuroscience and experimental psychology, we even examined fields where a whole bunch of smart and hardworking scientists seem to be making little progress towards explaining and predicting phenomena. Today we will think about the possibility that cognitive neuroscience and experimental psychology might not be the exceptions, but the rule. Perhaps most science is like that. Most science is a whole bunch of effort with very little to show for it. Indeed, part of the problems we encountered in cognitive neuroscience and experimental psychology appear to be manifestations of a larger issue plaguing many branches of science today. This issue is the low reproducibility of published results. Here's a list of the worst offenders. Cognitive neuroscience and experimental psychology need no introductions, and in the description of the previous lecture, I included links documenting the problem, especially specifically for experimental psychology. But they aren't alone. Clinical psychology and psychiatry also have abysmal rates of reproducibility. For instance, diagnostic reliability in these sciences are less than 20%. That means if you have a mental disorder and get comprehensive exams, the odds of receiving the same diagnosis from two different mental health professionals is about 1 in 7. What's more, studies investigating the effectiveness of various therapies are likewise hard to replicate. What looks like an effective therapy in one study might perform extremely badly in another. The same is the case with exercise and nutrition science and physical therapy. If you have a chronic injury or recurring back problems, you might have tried various physical therapists. In that case, you might have noticed that there are significant differences between the therapy regimens from therapist to therapist. This is due to the fact that the literature in this field doesn't present a clear picture of what would be an effective treatment for which injury. Quantitative studies in political science, sociology, and empirical economics are similarly problematic. Most of the time, a published result cannot be replicated by any other investigator. That's why there is so much disagreement about whether minimum wage laws help or hurt the working class, how to lower crime, and increase government effectiveness. I remember one distinct moment when this fact crystallized for me, the presidential debate between Barack Obama and Mitt Romney in 2012. Obama said, "I have 2 economic studies supporting the affordable health care." Romney replied, "I got 4 studies against it." Of course, politicians lie, but in this particular case, they were both telling the truth. Economists still can't agree about the impact of ACA on things like median income, employment, and GDP. And finally, there is the worst of the worst, pharmaceuticals, which will receive a detailed treatment in the next lecture, so stay tuned. The bottom line is this, though. Most of science seems to be in the middle of a rolling replication crisis. Most studies report results that cannot be reproduced. If you are wondering why this is happening, we will get to it today. But David Lycan already gave it away last time. The culprits behind the replication crisis in science are likely the null hypothesis significance testing and the practice of p-hacking it enables. What is the null hypothesis significance testing, or NHST for short? The short answer is that it's a method that is used to determine whether a result is statistically significant or not. But that's not very helpful in understanding why it would backfire and create a bunch of unreproducible results. To understand why, we need to dig deeper. We need to understand the fundamentals of probability and statistics. As I hinted earlier, When we discussed the common view and inductivism, I said most scientific inferences are statistical. That means they concern probabilities. A probability is the likelihood of a statement being true. Every probability is a number from 0 to 1, or from 0% to 100%. Statements that are guaranteed to be true have a probability of 1. Statements that are guaranteed to be false have a probability of 0. Of course, such statements are exceedingly rare. Most statements are somewhere in between. A randomly selected smoker will get lung cancer, for instance, has a probability of 0.2. Let's take a closer look at this probability to see how we can formalize it. Let the letter A stand for the statement, a randomly selected smoker will get lung cancer. Then you can express the probability as an equation, which reads the probability of A equals 0.2. Although they look different, these two expressions are saying the same thing. The one below is just a formal representation, which saves a little space and time. Another neat thing about probabilities is that they can be conditional. Consider the claim that the probability of Bob will be driving again given that he is in prison for life without parole is 0. The statement here is a conditional because it has the telltale phrase, given that. We can formalize it like this. Let the letter B stand for Bob will be driving again. And letter C stand for Bob is in prison for life without parole. Then you can express the same claim formally as probability of B given C equals 0. Notice the stroke sign in the middle. What comes after the stroke sign is the given condition. What comes before it is the statement whose probability is stated based on that condition. As you can imagine, in or outside science, most interesting probabilities are conditional probabilities. Even the earlier example was a conditional probability, although we formalized it like this. But that way of formalizing it hides the logical structure of the statement. After all, a randomly selected smoker will get lung cancer isn't a simple sentence. It's a conditional sentence. It means a randomly selected person will get lung cancer given that they smoke. Once we recognize that, we can let letter B stand for a randomly selected person will get lung cancer, and letter C stand for that randomly selected person smokes. Then we can state the same probability as probability of B given C equals 0.2. All these three expressions are saying the same thing. The one above is long, but more accessible. The one in the middle is short, but hides the logical structure of the statement. And the one on the bottom is both short and transparent about the fact that the statement is a conditional. What does that have to do with science, you might be wondering? This. You can also think about an experiment or observation in terms of conditional probabilities. Remember the solar eclipse experiment to test Einstein's general theory of relativity, for instance. Here, let H1 stand for Einstein's claim, massive objects span space-time. By the way, H1 is just how scientists symbolize the hypothesis being tested. It is like how mathematicians always call the variable x. It sounds fancy, but it is just a letter standing in for a statement. Then let the letter D stand for the data collected in the experiment, which is the apparent positions of the star nearest to the eclipse shifted by a certain degrees. Here's how you can think of Einstein's hypothesis given the results of the experiment. You should believe that hypothesis H1 if the probability of H1 given that data is high. And you might say you should disbelieve the hypothesis if the probability of the hypothesis given the data is low. Here's another example that should be familiar. the oil drop experiment by Millikan and Fletcher. Let H1 here stand for their claim all electrons have the same charge, which is roughly 1.6 times 10 to the power minus 19 coulombs. And here, let D stand for the data they got, which is the charges of all observed oil drops were multiples of 1.6 times 10 to the power minus 19 coulombs. One might say you should believe H1 if the probability of H1 given D is high. Similarly, one might also say you should disbelieve H1 if the probability of H1 given D is low. In other words, if the data you have make a hypothesis likely, believe that hypothesis. If the data you have make it unlikely, don't believe it. Wonderful, right? It is simple and straightforward. Except you already know that it won't work. You know it because Lakatos already explained why it won't work. He didn't use the language of probabilities, but the reasoning is easily transferable. This won't work because you never test a hypothesis by itself. You always condition your experiments and observations on a bunch of background assumptions, which Lakatos called auxiliary hypotheses. For instance, you should believe H1 if the probability of H1 giving your data plus a whole bunch of auxiliary hypotheses is high. And you should disbelieve H1 if the probability of H1 giving your data plus a whole bunch of auxiliary hypotheses is low. The problem here is that these probabilities are practically impossible to compute. So you cannot tell whether they are high or low. So the straightforward story about which hypotheses you should believe and which ones you shouldn't doesn't work because it is too naive. And Lakatos's more sophisticated version doesn't work because it requires you to know unknowable probabilities. It looks like we are stuck. We can't decide what to believe and what to disbelieve. Luckily, there was a smart mathematician in the room, this gentleman, Ronald Fisher. Fisher was an industrious and gifted statistician. He introduced, among other things, the concepts of the null hypothesis, or H null, and the p-value. And many people, including Fisher himself, thought that these concepts would help them bypass the problem Lakatos had. To see why they thought that, let's start with the null hypothesis. The null hypothesis, H null, is the opposite of H1. But it is the opposite in a very specific way. This probably sounds a bit mysterious now, but it will make sense in a second, I promise. Again, think about the oil drop experiment where H1 stands for the claim all electrons have the same charge, which is 1.6 times 10 to the minus 19 coulombs. God, how I wish I picked an example with a simpler number attached to it. Then H null would stand for not all electrons have the same charge. Electron charge is normally distributed. This part is easy to understand. Millikan and Fletcher say all electrons have the same charge, and H null says, nah, they don't. This is the bit that makes H null interesting and potentially useful. Electron charge is normally distributed. What does that mean? You might have never heard the term normal distribution before, but I guarantee to you that you know what it is. It's a bell curve. A lot of things are normally distributed. IQ, for instance, is normally distributed. The average is 100 points, and most people are near that. Very high IQ and very low IQ people are exceedingly rare. That's why if you tally all people's IQs and graph them, it would look like a bell curve. Height is also normally distributed. Most people are close to average height. Very short and very tall people are very rare. Philosophical and artistic talent, if we can quantify them, may also turn out to be normally distributed. But what does that have to do with electrons? Let's call that number E so that I don't have to say it a bunch of times more. If H null is true, then E, the charge Millikan and Fletcher falsely claim to be the universal charge of all electrons, is somewhere in this curve. Let's say here. Under this bell curve, there is an imaginary heap containing all the electrons in the universe, ordered by charge. On the leftmost, there are very negatively charged electrons. On the rightmost side, there are less negatively charged electrons. And all the electrons that have charge E are in this infinitely thin red strip. But in that case, something weird is going on, because remember, the charges of all the drops Millikan and Fletcher observed were multiples of E. But that's nuts, because the overwhelming majority of the electrons are somewhere else in the curve in this green shaded area. This would be like randomly selecting 58 people around the world and measuring their heights, and all of them being 30 inches tall, 60 inches tall, or 90 inches tall. What are the odds? In formal terms, the probability of getting the data Millikan and Fletcher got is exceedingly low, given that the electron charge would be normally distributed. Fisher calls this probability the probability of data given the null hypothesis, the p-value. The p-value is what Fisher uses to test a hypothesis for statistical significance. Here's how that test is done. For a hypothesis H1 and data D, the scientists calculate the p-value. If the p-value is less than 0.05, H1 is statistically significant. If the p-value is equal to or greater than 0.05, H1 is statistically insignificant. And that is the standard by which most publication decisions are made in those disciplines. Most journals in these disciplines publish a result if it is statistically significant and reject it if it is statistically insignificant. But let's not get ahead of ourselves. Just the fact that the disciplines where NHST, in other words, statistical significance, is used as the primary publication criterion, have abysmal reproducible rates, doesn't establish that NHST is responsible for the replication crisis. Indeed, we need more to pin this one on NHST. And don't worry, I'll give you more. Let's think about a hypothetical pharmaceutical study where scientists randomly selected a chemical compound and they are testing the hypothesis that this compound would be effective in treating cancer. So that's our H1. H0 is the opposite. It says this compound is ineffective in treating cancer. Suppose these hypothetical scientists press on with their experiment and collect the following data. They gave 20 randomly selected people, cancer patients, this randomly selected compound. And they survived 3 months longer than the patients receiving other therapies. To learn how to calculate the p-value, you need to go take a statistics class because there is some wizardry happening in the background. But suppose I tell you that the p-value is low. Let's say it is 0.02, which is much lower than the 0.05 threshold, which is the threshold for statistical significance. So the result is statistically significant. You can go publish it in a journal and be interviewed by New York Times for inventing a new cancer drug. But if I'm a cancer patient, or a smart cancer patient at least, I wouldn't care about the p-value or your fancy New York Times interview. The probability I would care about wouldn't be the probability of this data happening given that you were wrong. What I would want to know would be this. What is the probability that you are right given the data? At this point, most people would say, well, it's got to be high, right? Because after all, what are the odds? Here's how most people think. They say the p-value is very low. What are the odds that this is a coincidence? What are the odds of those people surviving longer if XYZ did nothing? So, XYZ must be doing something. Therefore, the probability of H1, given the data, must be high. I regret to inform you that most people, as usual, are wrong. To understand the fallacy in the previous inference, from statistical significance to high probability of a hypothesis, let's think about what would happen if all scientists did was to randomly pick compounds and try them on cancer patients. We are going to imagine a world where they test every possible compound. But before we get ourselves more confused than we already might be, let's write down what is known. H1 is the hypothesis being tested, that the compound works. H null is the opposite, the compound doesn't work. D stands for the data that 20 people lived longer when given the compound as a drug. The p-value, the odds of this happening if the compound doesn't work, is very low. Then, what is the probability that a randomly chosen compound is actually effective if people live longer while on it? You can answer this question using a theorem called Bayes' theorem. But that will mean a bunch more jargon. No one has time or patience for that. So let's imagine the possibilities. Remember, scientists look at all the compounds in the world and tested them one by one on cancer patients. The first possibility is that we try a compound on a group of 20 patients and they live longer. But the opposite can also happen. They might not live longer. Then there is a question whether a tested compound is actually effective or not. You might expect a drug that is actually effective to work. So you might think all the outcomes in the first column are going to be here. But that's not necessarily true. Even if the drug is effective, the people in the sample might not live longer, just by tough luck. Maybe, just by misfortune, scientists picked an odd group of 20 people, and if a few of them were severely allergic to the compound, and as a result of therapy, their immune systems got overwhelmed by the drug, and they declined faster than the control group. That might be enough to bring down the sample average enough to make it lower than the control. There's also the possibility that the compound isn't effective. Like in the previous case, you might expect that everyone who received an ineffective compound would die faster than the control. But not necessarily. Sometimes you get lucky. Cancer patients, on occasion, spontaneously go into remission. This is very rare, but it is not impossible that your sample has some such people in it. That would increase the measured survival time for your sample. So on the left column, there are all the outcomes corresponding to effective compounds. And on the right-hand column, we have all the outcomes for ineffective compounds. The top row are the compounds with which samples survive longer. And you get it. Now remember compound XYZ from the previous example. 20 people, we said, did survive longer on it. So it is somewhere in this row. When we ask what is the probability that it is effective given that 20 people survive longer on it, we are asking what are the odds that XYZ is in the square on the left. It might look hopeless, but I promise we are going to figure it out. Let's start with a chemistry question. How many possible chemical compounds are there? Here, I'm not just talking about natural compounds, I'm also talking about compounds we can synthesize in a lab. It's hard to be exact, but millions is the correct answer. Most estimates range between 3 to 6 million. To make it a nice round number, let's say 5 million. So if we counted all the compounds in each square and added those numbers up, it would be 5 million in total. So that we don't forget it, let's add that to our list of givens. Then another question. how many compounds could actually be effective in treating cancer? Again, it's hard to be sure, but it is bound to be a small number. If it were high, after all, it wouldn't be so hard to discover new cancer drugs. So let's say there are 5,000 compounds in the nature or can be synthesized in a lab total that actually are effective in cancer treatment. Let's put that in our notes as well. We said the total number of all compounds on the table is 5 million. And only 5,000 of them are in the left-hand side column. That means 4,995,000 of them are in the right-hand side. Let's write that down as well. Remember, the p-value is low. The chances of a compound seeming effective in experiment, while in reality it isn't, is 0.02. That is to say, number k is just 2% of all the ineffective compounds. And remember, we know how many ineffective compounds there are. Compute the 2% of that, and you get just shy of 100,000. Let's write that down in the table. Now imagine an ideal world where there are no false negatives. That is to say, every effective compound appears to work when tested. So, what I'm saying is n is 0. Let's write that down. We know that the sum n plus n is 5,000. And m is 0. So n must be 5,000. Let's again write it down. If you have an obsessive compulsive personality, we can figure out what J is. But we don't need to. We are already there. We are ready to compute the probability we have been after all along. The probability that XYZ is actually effective given that scientists tested it in a lab and 20 cancer patients lived longer on it. Since D is true for XYZ, it must be somewhere in the top row. What we are wondering is the probability that it is in the good side, the left side of the top row. You can estimate that probability just by using these two numbers. This situation is just like this. You are going to play the lottery. There are 5,000 winning tickets. There are 99,900 losing tickets. You buy one ticket at random. What are the chances that you will win? This is the total number of tickets. There are 5,000 scenarios in which you will win. So the chances of winning is this, just shy of 5%. That is terrible. Remember how I said most people think since the result is statistically significant, the result is likely true? This is why those people are wrong. If a big chunk of what is said flew over your head, don't worry, not everyone has to understand mathematics. Let me give you just the moral of the story. Statistical significance doesn't mean anything, especially when the hypothesis that is being tested was randomly selected from a large set of possible hypotheses. And this is largely why these disciplines are undergoing a replication crisis. There are only three things common in between them. They all study complex phenomena involving innumerably many variables that can be chosen at random and be investigated. They primarily rely on statistical significance as the publication criterion. And finally, most published results in these disciplines cannot be replicated. Indeed, a significant number of scientists in these disciplines commit what is called p-hacking. What is p-hacking? It is this. They go out, collect large amounts of data pertaining to many variables. Then they use statistical software to quickly look for hypotheses with low p-values. And then they publish all their results, usually one by one. In other words, these scientists generate an endless stream of junk science. As you can tell, most of these results are false. That's why there's a replication crisis. What can we learn from all this? First, perhaps most of science today is epistemically suspect. The prevalence of p-hacking is an especially strong indication that the results reported in a discipline cannot be taken at face value. Nonetheless, grasping the difference between p-hacking and respectable forms of science is difficult. Once again, there is no fast and easy way of distinguishing good science and junk science, as the messiness of my explanations illustrate clearly. But this mercifully brings me to the end of this lecture. Send me an email if you have any questions. Thank you for your patience, and I'll catch you next time.